Hey everyone, welcome to another screencast. Today we're going to go over Chapter 17, Blueprint Reading for Facility Maintenance Technicians. So, by the end of the chapter, you're going to be able to do a few things. Number 1, identify the various views of an orthographic drawing. Number 2, identify the various symbols used on plumbing plans to represent piping types, fittings, and symbols on a plumbing plan. Number 3, identify the various symbols used on HVAC plans to represent HVAC line types, ducts, and equipment. And finally, identify the various symbols used on electrical plans to represent wiring, switches, fixtures, and so on. You'll also be able to understand abbreviations and symbols used on blueprints. This one is probably the most important. Determine the length of objects presented on a blueprint using an architect's scale and/or tape measure. Determine the angle of a line on a blueprint using a protractor, and understand abbreviations and symbols using a blueprint. So when we look here, this is an architect's scale. We're going to be going over how to use it. We read these just like anything else. We start over here on the left and then read up to the right. Everything is done in lines. So I'm not sure if you've seen a drawing like this before. Blueprints, basically, just diagrams. And now we're going to learn how to draw them and how to make sure that they're drawn properly. So a linear measurement is defined as a measurement of 2 points along a straight line. So anytime you have 1 point here and 1 point here, if you draw in between here, that will end up being a straight line. Currently, there's 2 basic systems for this. The English system of measurement, which we use quite a bit, and the metric system of measurement. So for us, we're just going to be focused on the English system of measurement. The metric system, you can read this on your own time. We do not use these in the lab at all. Everything that we do is done in English or standard. So this is what we use. The English system, it's based on feet and inches with fractional increments. Now keep in mind, when we do these, we went over this in lab a little bit. So we will use halves, quarters, eighths, and sixteenths. That's it. Every inch is typically broken into 16 parts or sixteenths. Each 16th increment has a name. So let's check out what linear measurement looks like when we're reading a blueprint. So for some of you, on one of the performance assessments, you had to draw the entire lab, right? And that's a dimension drawing. And what I had you do is draw the overall length. So we had our lab here, overall length, and then we had to do width of 3 different areas as well. So the architect's scale is a type of ruler. It has ranges of pre-calibrated ratios, and they're made of a variety of materials. So we have ones that are plastic, we have ones that are wood. The ones that we have, we're going to go over in more detail, so don't get too caught up on the details that this presentation has. The most commonly used architect scale is the triangular scale, and those are the ones that we have in class. The flat scale, which is illustrated here, we don't use, so don't worry about it. Angular measurement, we're not going to get too much into this right now, so don't stress over it. Just know that there's degrees, radians, and gradients. And we can use that for reading and measuring angles. So here's an example of some of the HVAC abbreviations. So an exposed radiator, recessed radiator, flush enclosed radiator. Don't get too caught up on this. If you need to, use this slide as a reference, but we're not going to go into detail on specific plans or specific abbreviations at this time. The point of this is to give a general overview and how to read, how to draw. So here's some more architectural symbols, and these are just more examples. We may be using some of these next marking period. The ones that we won't be using are all of them from down here. So these we don't need to worry about. So let's make this all of these we don't need. But what's nice is, as it says here, it's a shorthand method of communicating information. So the blueprints that we have, it's a very small area, right? And we don't want to go and write out everything because it's going to be too jammed up with words and it's going to be confusing to read. So instead of that, we take symbols and we read symbols. Some of those symbols include door symbols, window symbols, how materials are arranged, how different appliances are arranged, and different applications that may be needed. So written specifications, you're going to see these. This is the block that has all the information on it, so it lets you know the date, what scale you're using, who drew it, who checked it, things like that. And they're created by one of or all of the following. So it can be the architect who does it, it can be the engineer, the contractor, or even the client. So specifications are created that will cover or describe in detail the product requirements or details, right? So let's say that you're going to do a kitchen and someone says, oh, well, I want to put a stove in, or I want to put a refrigerator in. Well, that all has to be outlined. In addition to that, the type of windows, the type of doors, the type of flooring, the type of wall covering, the type of wall framing. So anything that gets built needs to have the requirements and details in it. It needs to meet certain specifications. It also has the material that you need to use. So, for example, if you're going to frame a wall, you don't want to do it out of toothpicks, right? We're going to use framing lumber that we have here, which is going to be either 2x6 or 2x4. The workmanship requirements, so I hold you to this standard also. Usually I have it to within 1/8 or 1/16 of an inch, and also the finish must be to industry standard. So it has to be something that you can get paid to do, not just something that you slap together to say that you got it done. The specifications must be concise, clear, well written, and to the point. We don't want any fluff. Let's cut out all the fluff and just say, this is what you're doing, this is how it's getting done, and that's it. And then that way the builder and the customer can both agree on it. For two-dimensional views, they are the most common method of representing objects on engineering and architectural drawings. So if we're using paper's two-dimensional, so it becomes fairly difficult to make a three-dimensional representation on a two-dimensional surface. To overcome that, we have multi-view drawings. So we have additional views that are created. They are created to reveal all the hidden attributes of the part, and very complex parts might contain views showing the front, sides, back, bottom, and top of the object. So generally in here, what I'm going to have you do is a top view. So imagine whatever you're building, that you take a drone and fly it up over the top of the drone, or sorry, the wall or whatever you're building. And that's the top view, right? So it's you looking down at whatever you're building. You're also going to do the front view, so as if you're walking right into it. And then you're also going to do the side view, that if you're walking to it, you turn, up, there it is. So keep those in mind. Those are 3 drawings that you're most likely going to have to do here. So here we have axonometric projections. These include pictorial drawings. The object is rotated so that all 3 dimensions are seen at once. So we're not going to do this. This becomes a little bit difficult. You also have to draw these at specific angles. Generally, they're 30-degree angles. Don't worry about that. Just know that they exist. So when you do these, you can have the length, width, and depth all at the same time. So this is a good representation of what it may look like. It's helpful when a non-technical person is trying to visualize what a part is going to look like. So if I'm looking at this and I'm looking at this, I already have a general idea of what it's going to look like, right? This is a good top view. I might ask for a front view or a side view. Alternately, you can also have the pictorial views, where it gives you a better demonstration of what that looks like. Oblique projections. So this is a form of pictorial drawing. This is the one that I was talking about. The projection plane is set parallel with the front surface of the object. The line of sight is at an angle to the projection plane, so generally this is at 30 degrees. They're similar to an isometric because all 3 axes are shown. The front of the object is not rotated. So you're looking at it just the way that it is, and it's only drawn on an angle so that you can see three-dimension detail. The front is drawn at full scale, but because we're drawing everything on an angle, it would become exceedingly difficult to scale everything that's on the angle. Perspective projections. Give the object a more natural appearance. Allows the projection lines to converge to a single point. So we're not going to have to worry about this. This is like when you see it and it fades into the distance. This type of drawing is more commonly used in the art world. These drawings are especially helpful if a presentation is to be given to a group of non-technical persons. So you know when you go and you look down a hallway where everything gets smaller as it goes down? At least it appears that way, and that's what a perspective projection is like. So it gives you the idea that there's length, there's width, there's depth to whatever we're looking at, and it changes by perspective. Here we have auxiliary views. So it uses orthographic techniques, produces a projection on the plane other than one of the three principal planes. Its purpose is to show the true shape, size, and/or length of features. The view would otherwise be foreshortened in the principal views. So here we have a top view, a front view, and a right side view. Now, when we look at the auxiliary view, we can see there's a lot more detail in here than what the top view shows, what the front view shows, and what the right side view shows. Floor plans. So these are great. These are where we're really going to focus. You will absolutely fall in love with these. So floor plans are the skeleton or framework for the development of other drawings required to complete the construction of the structure. So there's several types. So we have electrical plans, fire protection plans, framing plans, plumbing plans, and HVAC or mechanical plans. For elevations, it's an orthographic drawing. So what we're doing is showing one side of the building and just saying, oh, well, this is this height from this. Oh, this is this height from this. It's important to realize that between each elevation projection and the plan view is an imaginary 90-degree folded line. Elevations are shown to exterior shapes and finishes. Dimensioning. Oh, this is great. This is, besides floor plans, this is probably my favorite. So, unidirectional dimensioning, we're just dimensioning in one direction. Aligned dimensioning, tabular dimensioning, hourless dimensioning, chart dimensioning, baseline dimensioning, and chain dimensioning. So, let me help with all of this. And let's just focus on dimensioning. So all we're doing when we're dimensioning is putting measurements to a drawing that we have, and that's the idea behind drawing it to scale. So on here, all we do is add our dimensions to these things. It's not so bad. They have a lot of stuff in here that it's not important for what we do in the lab right now. Material takeoffs. So all of you will be doing this. This is the basis of an estimate. So you create a list of materials. It includes the quantities and types needed to complete a project. They're generated from the construction drawings and documents. So you should be able to convert concrete volumes into cubic yards and use linear feet measurements for dimensional number. We're going to go over this in more detail in the following weeks. The idea is that you take a drawing. It doesn't matter what the drawing is. If it's dimensioned, you'll be able to figure out whatever material that you're going to need for whatever you're building. So if you're looking at a wall, it's like, oh, this wall is 8 by 10. Well, we're going to find out how to get all of the material that you need for that 8 by 10 wall. Building codes. So these are important. We adhere to the Uniform Construction Codes, UCC. You need to build stuff to a certain standard, right? You just don't want to throw stuff together. It has to be neat. It has to be done in a way that's approved. If it's not, you tear it out. And the last thing you want to do is tear out. If you do tear out, then you're paying for it rather than someone paying you. So, for example, if you're going to frame out a wall and you decide to frame it on 18-inch centers when the drawing clearly indicates it should be 16-inch centers, guess what? Not good. Chances of you having to add more wood or even rip it out increase. And who wants to do rework? Not me. So do it right the first time. Don't try to cut corners. Make sure you adhere to these guidelines. So building codes define the standards that regulate the construction of a building. Again, we just can't go and throw stuff up together, right? Maybe you guys did that before. Maybe if you're building a tree house or a clubhouse or something like that, it doesn't really matter. But in here, it's going to be what we do in the real world. So we do have codes that we need to follow. Sheet metal. So this isn't important. We don't need to worry about that right now. Same with this. So, as a quick summary, linear measurement is the measurement of 2 points along a straight line, right? Dot, dot, psh, straight line. All objects consist of points and lines. In the HVAC industry, a point can be the center location of a gas line or the edge of a rectangular duct. Don't worry about that. Since the circumference of any circle contains 360 degrees, an angular degree is equivalent to 1/360th of the circumference of a circle. Don't worry about those. The circumference of any circle contains too much math. A radian, don't like that word. Too much math. To convert too much math. In a first angle projection, the top view is generated by projecting the object's contours down onto a horizontal plane. The right side view is generated by projecting the right side of the object through the object to the profile plane. What does that mean? We're going to go over this in a way that actually makes sense. So don't stress over this. In a trimetric, don't need to worry about that one either. That's it. So we're going to go in more detail about what this looks like and really apply it to what we're doing here. Not only what we do in lab, but what you're going to be building. So this is going to be done for walls. It's going to be done for your floors. It's going to be done for your framing. It's going to be done for your roof. It's going to be done for the siding, brick veneer. Everything that we do in here, we're going to have drawings. And the reason that you do drawings is because I want to know that you know how to measure, and I also want to know that you're able to do the basic math necessary to project costs out. And that's how you can be competitive. So, thank you for watching.